Hello, my name is Paarth Rathore, and I'm presenting the Aerospace Attitute Control Investigation Project. My mentor is Nate Osikoves, and I chose this topic because of my strong interest in aerospace engineering and drones. And I'm presenting this from Atlanta, Georgia. At the time of recording this, I have not finished the project yet, however, I'm about halfway through it. So a quick overview of quadcopters. Quadcopters are UAVs with four propellers are becoming increasingly more popular due to their versatile applications, such as in military operations, surveillance, environmental mapping, delivery, etc. Their lightweight design, speed, and autonomous operations make them invaluable to our current world, and it's only becoming more vital as this technology is advancing. So the focus of my project was to take this quadcopter and to simplify it down to a seesaw. A quadcopter has four propellers, while my seesaw model will have two propellers, one on either end, and these propellers will work together to maintain balance on the seesaw if the seesaw is ever off balance, either whether it's tipped on purpose or by accident. I plan to collect data on the seesaw model on different factors. So these factors are what material a seesaw is made out of, whether it be wood, metal, plastic, how does that affect the balancing time and the stability of the seesaw, as well as the length. How does the length affect the balancing time and the stability? And this will help us understand on how these elements could affect actual quadcopters' efficiency, reliability, and the quadcopters' balancing time and stability. So, first, I have to develop an algorithm that will actually balance the seesaw. This is going to be done through a closed-loop control system and using PD control. PD standing for proportional and derivative control. I have not built the algorithm yet for the seesaw. However, I have developed an algorithm for the spring mass damper system, which uses the exact same concepts as the spring mass damper is a simpler example. And I'll be using what I've learned with the spring mass damper system and apply that to the seesaw. So, the actual test stand itself. So, to actually test our data, I've created a test stand that'll have the seesaw in the middle where we can test all our data. It'll also have a breadboard right at the center of the test stand, which will be equipped with an Arduino Nano and an MPU 6050 sensor. This sensor has a gyroscope in it, as well as an accelerometer. So what will happen is that this sensor will collect necessary data, the angle that the seesaw itself is at, as well as its velocity, acceleration, and position. The position will come from the gyroscope, and this data will go to the Arduino Nano. The Arduino Nano has code in it that I've coded in Python and Arduino code combined with the algorithm as I mentioned earlier, and this will all work to help balance the seesaw out. This is how the algorithm itself will be implemented, and then we can adjust our factors like the material and the length, as I mentioned earlier, and this can be done to test and see what results come about the balancing time as well as the stability. Before applying the algorithm to the test stand itself, though, I will first simulate the algorithm, which is absolutely crucial in aerospace. That's because you want to make sure your simulation that your algorithm actually works, as to avoid critical failures in real life. So in conclusion, as I progress, I will be finalizing my algorithm, simulating its performance, and conducting tests, and then analyzing my results from those tests as well. My research aims to contribute to quadcopter technology by exploring different variables that affect performance. I hope this work will also help others get started with quadcopter software and control theory, ultimately fostering innovation in aerospace engineering. Thank you for listening.